Now that you understand the process of gene transfer, we're going to talk about how it relates to drug resistance. As you're aware, and we've talked about with our little guy MRSA, the superbug, we know that antibiotic resistance is a big problem, okay? We are edging on what we are referring to as a post-antibiotic era, meaning a lot of the antibiotics that we have, the organisms are developing resistance to, and the antibiotics are no longer going to be useful. The different types of resistance that we're going to talk about briefly are intrinsic, chromosomal, and plasmid mediated. Intrinsic is the easiest, and we've talked about it already. You may not have realized it. But for example, Mycoplasma is resistant to penicillin. Why? Because it doesn't have a cell wall. That's an intrinsic property of Mycoplasma that renders it resistant to penicillin. All right? Chromosomal mediated is when the resistance, of course, is encoded on the chromosome. And the most common example here is when you get modification of receptors for drugs so that the drugs can no longer bind to the organism. In the case of the penicillin binding protein is a good example here. In general, chromosomal-mediated resistance is fairly low level, but again, our good friend methicillin-resistant staph is a good example of when it's the exception to the rule. Low level can be clinically significant because Streptococcus pneumoniae, for example, has chromosomal-mediated resistance, for example, in the case of meningitis, but we know that this is clinically significant. Now finally, plasmid-mediated, this is what we've talked about for quite a bit now. This is probably the most common way and the simplest way that bacteria acquire drug resistance, where the resistance is located on the plasmid, and then very easily through conjugation, we can transfer the plasmid from one bacteria to another. So now instead of calling the plasmid an F factor or fertility factor, if it encodes for resistance genes, we're going to call it an R factor or a resistance factor. Now, what is alarming is that on an R factor, you can see resistance cassettes for multiple different antibiotics now, not just one, okay? So they can encode for multiple antibiotic resistance via the addition of transposons. So we insert a cassette for resistance, and then another one, and before too long, one nasty conjugation event can now render a bacteria multi-drug resistant. So, how do these multiple drug resistance plasmids arise? Through the integration of the transposon, i.e. integron, or gene cassettes. Okay, so we may use those terms interchangeably. They're not 100% interchangeable, but what we're talking about are mobile genetic elements. They can jump from one piece of DNA to another. They are not only found in bacteria, but viruses and eukaryotes as well. And one of the features of the mobile genetic elements is they have indirect repeats on each end, which means that the indirect repeats, we're reading the DNA the same, but in the opposite direction. They also carry a transposase enzyme that aids in the transposition, in nicking the DNA and allowing for the insertion of the DNA. They do create mutations when they insert. Clearly, they're breaking up perhaps a gene. And the insertion, as I'm about to show you, produces direct repeats on either side of the transposon. So I'm going to show you a little animation on transposition, basically just showing you one step at a time what occurs with transposition. Same figure that you have in your book, just a little bit more animated. So this is the most simple example of a transposon where you have the genes necessary for transposition and you have the indirect repeats. Okay, so indirect repeats we're reading the same way this way and then indirectly again on the opposite end. So that's the minimal requirement for transposition. Now, The bacterial DNA where we're going to insert is cleaved by the gene encoded by the transposon called the transposase. And now we're going to insert that transposon into the bacterial DNA. In doing so, what we're going to have to do is repair these junctions, and in the process of that repair, we're going to wind up flanking the indirect repeats with direct repeats. Okay? So that's what's going to happen when a transposon moves from one piece of DNA to another. Now, clearly, if we're just talking about a transposon with nothing else on there, it's not really alarming. What we worry about, of course, is that transposon now carrying a bit of drug resistance, all right? And this is how, again, multi-drug resistant organisms easily arise. So how does this happen easily? Let's just look at this. If we have a transposition event where we're taking a resistance cassette and inserting it into chromosomal DNA, then that chromosomal DNA is integrated with another resistance cassette. We'll call it B. Now we have an AB cassette on a stretch of DNA, and now we get integrated with another resistance cassette. Now what's going to happen there is now with one conjugative event, we're going to transfer multiple drug resistance, okay? Through this process of transposition and integration happening on multiple levels, you can now see that one conjugation event with this R factor now encoding for multiple drug resistance with one event can be transferred from one cell to another. So you can see how easy that is for the bacteria, which explains why it's happening so quickly. This just shows you an example of one of the resistance transfer factors with the determinants on there. For example, you have the R factor with an insertion sequence here for chloramphenicol, streptomycin, sulfonamides, and ampicillins, kanamycin, neomycin, okay? So multiple drug resistance on one plasmid. Again, very, very dangerous, because we know through the process of conjugation, especially going from F plus to F minus, what happens? All of the cells in that cross become F plus and are going to have that resistance plasmid. The next table that we're going to be looking at really just speaks to some of the plasmid-mediated mechanisms as far as antimicrobial resistance. So for example here, penicillins and cephalosporins. What's the mechanism of resistance? We've talked about this quite frequently, but it's the beta-lactamase. So it cleaves that beta-lactam ring, and so through the production of the beta-lactamase can you get resistance to the penicillins and cephalosporins. And this basically is just listing some of the other drugs by either via production of acetyltransferases and inactivation of the drug by acetylation are some of the mechanisms that we're talking about transferring. Again, this is just continuing on the list with the tetracycline, sulfonamides, and vancomycin. I think clearly that penicillins and cephalosporins are going to be important here, and vancomycin is also going to be an important one that you should probably hone in on. And that the mechanism of resistance is that we get mediated change into peptidoglycan, so vancomycin can no longer bind. Okay, so you don't want to memorize all of these different mechanisms, but probably the ones that are most clinically significant. Now, transfer of drug resistance for Neisseria gonorrhea. This one's a little bit interesting. It's a little bit different. We know that gonorrhea has drug resistance. Again, the protocols for treatment change all the time for Neisseria gonorrhea. But we're talking about here what's called a non-conjugative plasmid. It has lost the ability to direct conjugation. It's lost the transfer operon. But it has retained its ORET, its origin of transfer. So if another fertility factor gets into the cell with this non-conjugative plasmid, you get trans-acting help, and as long as that non-conjugative plasmid has an ORI-T, now with the help of an additional plasmid that can supply that non-conjugative plasmid what it needs in trans, it can be transferred as well. And that process is referred to as mobilization. So that's an important mechanism of microbial resistance, antimicrobial resistance, that you should be aware of for Neisseria gonorrhea. Now, Staph aureus, we're back to our superbug MRSA. Okay? Now, initially, the methicillin resistance for this little guy was acquired by transduction. It was chromosomal mediated, and we had a transduction event that took it from one cell to another. But now we know that we have vancomycin resistant staph, intermediate vancomycin resistant staph, and the staph in this case, the superbug MRSA, acquired the vancomycin resistance from Enterococcus on a multiple drug-resistant plasmid that was donated by its good friend Enterococcus. Now the super multi-drug resistant, hence our little superbug here, dun, 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 dun. He's the superbug, okay, has resistance not only to methicillin, but to beta-lactams, vancomycin, aminoglycosides, trimethoprim, and even some disinfectants. So it really has become a superbug, one you definitely don't want to come in contact with. Now, as far as gram-negative transfer of drug resistance, typically it's plasmid mediated and it's accomplished by way of conjugation. Okay, so that one's fairly simple, and I think we spent a pretty good deal of time talking about conjugation, so you should be comfortable with that. Selection and transfer of drug resistance genes. Again, we're looking at three mechanisms here. Chromosomal mediated resistance, where you're selecting for the mutants or the mutations. Okay. Plasmid mediated resistance, where you're spreading that resistance factor, that R factor. Additionally, plasmid mediated resistance, where you're just spreading the resistance gene. Okay. So those are some of the selection and transfer of drug resistance genes and some of the different mechanisms by which that can occur.